Whether you're modeling an urban drainage system, a flood-prone catchment, or a storage-controlled network, the routing method and parameters you choose determine how water moves through your model. In SWMM, you're not limited to one approach. You can use a steady flow, kinematic wave, or the fully dynamic wave method, each based on very different assumptions and suited to very different problems. In this video, we will explore the theory behind each method, their key parameters and assumptions, what they are capable of, and finally the common mistakes modelers may make so you can confidently choose the right routing option for your model. Let's get started. The SWMM model was first developed between 1969 and 1971 under the sponsorship of the US Environmental Protection Agency, EPA. SWMM is a dynamic rainfall runoff simulation model used primarily for urban areas. It treats a drainage system as a set of subcatchments that flow into a network of pipes and channels. SWMM offers several routing options, and the selection of a method is not merely a computational preference. It's a fundamental engineering decision that dictates the theoretical validity of the simulation. Let's start with channel routing options. SWMM offers three channel routing options. First is the steady flow routing. It represents the most simplified level of hydraulic simulation available in SWMM. It ignores the inertial and pressure terms of the momentum equation. The other governing assumption is that the time scale of flow changes is sufficiently large relative to the travel time through the conduit. This means the storage term ds over dt in the continuity equation can be ignored for routing. Therefore, it inherently ignores the attenuation of the flood wave. The inflow hydrograph entering the upstream node of a conduit is instantaneously translated to the downstream node without any change in shape, magnitude, or timing, provided the conduit has sufficient capacity to convey the flow. Fundamentally, this is a rigid translation method often described in the literature as cascade routing. This method assumes that flow is uniform and steady within each computational time step. It uses Manning's equation to calculate the flow depth under normal flow conditions, SF equal to S naught. The computed flow is compared against the conduit's full flow capacity Q full. If the inflow exceeds this capacity, the flow is capped at Q full. The excess volume is either lost from the system, leading to continuity errors, or ponded atop the inlet node depending on the user's allow ponding setting. The limitations of this method are as follows. First, there is no attenuation, therefore it almost always overestimates peak flows in large networks. Second, steady flow routing is theoretically valid only for dendritic or tree-like networks where flow moves in a single direction towards an outlet. It cannot handle loop networks or flow reversals because the required terms are missing from the momentum equation. Thirdly, the method assumes normal flow at all times and therefore cannot handle backwater effects. Finally, steady flow routing is largely insensitive to the time step. This makes it computationally efficient but theoretically disconnected from the physical celerity of the wave. This method is suitable for the following scenarios. First, preliminary pipe sizing, where rapid and conservative estimation of maximum pipe sizes is acceptable. Second is for long-term continuous simulation, when analyzing total runoff volumes are desired rather than instantaneous peak flood stages. This is because the timing errors of a steady flow may be negligible compared to the computational speed gains. Finally, for the diagnostic screening, this method serves as an effective tool for identifying gross continuity errors or network connection issues before engaging more complex routing options. A frequent error in the application of SWMM's steady flow option is its use on flat terrain. In very flat areas where the slope approaches zero, the calculated capacity via Manning's equation also approaches zero. This leads to artificial bottlenecks and phantom flooding at nodes, even if the conduit is large. In reality, flow in flat conduits is driven by the pressure gradient, a term from the momentum equation that steady flow routing explicitly ignores. The kinematic wave equation is derived by retaining the continuity equation in its full form, but simplifying the momentum equation by neglecting the inertial and pressure terms. It assumes a balance between gravity and friction forces and uses the Manning's equation to express flow rate Q as a function of cross-sectional area A. Substituting this relationship into the continuity equation yields the kinematic wave equation. SWMM employs a spatially lumped nonlinear reservoir formulation for each conduit solved via a finite difference scheme. This approach balances accuracy with numerical stability. A theoretical kinematic wave propagates without attenuation. However, in practice, the SWMM's kinematic wave routing produces attenuation. This is an artifact known as numerical diffusion caused by the finite difference approximation. While theoretically an error, this numerical diffusion often mimics the physical diffusion or attenuation observed in real rivers. Since the momentum equation in this method is simplified, the accuracy of kinematic wave routing depends heavily on the parameters, the stage-discharge relationship. These parameters are as follows. First, the channel slope. A critical and often overlooked limitation in SWMM's kinematic wave engine is that adverse slopes or negative slopes are strictly prohibited. Second, the Manning's roughness. It controls the friction and consequently the celerity of the wave. The other parameter is the subcatchment width or W. For the overland flow component, which uses a kinematic wave formulation on a plane, the width parameter is the single most sensitive calibration knob. It defines the length of the overland flow path L, which is equal to area divided by width. Users often misinterpret this as the physical width of the catchment. In SWMM, it is a shape factor. Increasing W decreases the overland flow path length, reducing the time of concentration and producing a sharper, higher peak. This parameter is functionally similar to optimizing the K parameter in Muskingum routing. The limitations of this method are as follows: no backwater effects, no pressurized flow, no adverse slopes, dendritic networks only, and finally the stability versus accuracy challenge. While generally stable due to the implicit solver, kinematic wave can suffer from excessive numerical dispersion if the time step is too large relative to the conduit length. This can lead to underestimated peak flows. This method is best for steep catchments where gravity forces dominate inertia and pressure forces, and for long-term simulations, as kinematic wave offers an optimal compromise between computational speed and volumetric accuracy. The common mistakes in these methods are as follows. First, the time step selection. Although the implicit kinematic wave solver is stable, large time steps can cause significant continuity errors. Next is about misunderstanding ponding. In kinematic wave, if flow exceeds Q full, the excess water must be stored. If allow ponding is turned off, this water is simply deleted from the simulation, reported as a continuity error. If turned on, it stacks vertically at the node. Users often mistake this vertical stacking for physical flooding. In reality, it is a bookkeeping storage mechanism unless the node is explicitly modeled with a ponded area to mimic a reservoir. The foundation of dynamic wave routing is the full one-dimensional Sandbanon equations. By retaining all terms, it allows the simulation of backwater effect, flow reversals, and inertial effects. SWMM uses a successive approximation method, often termed as modified Euler method or Picard iteration, to solve these equations. It's an explicit finite difference scheme, meaning that the modeler generally cannot choose an arbitrary time step. Instead, the time step must be dynamic and often extremely small, on the order of seconds, to maintain stability. The dynamic wave method is best for tidal outfalls, flat terrains, network loops, and surcharge systems. One of the common mistakes in this method is dry bed instability. Dynamic wave equations become unstable as water depth approaches zero. To avoid this, ensure defining proper minimum nodal surface area and check for negative slopes or drops in the system. Dynamic wave routing is the most expensive method computationally. Justifying its use requires identifying specific hydraulic phenomena in the system that kinematic wave cannot simulate. Use this table to better compare the capabilities of each routing method. Let's move to SWMM reservoir routing. The reservoir routing in this model is handled by a storage unit. Following the level pool routing concept, the storage unit uses the continuity equation for reservoir routing. To know more about the level pool routing, please watch our tutorial on this method. Here, both the storage and outflow are assumed as a function of water level H at each time step. Despite having similar theory and assumptions to level pool routing, SWMM employs a different calculation engine. Here the model solved this nonlinear equation iteratively using Newton-Raphson's method at each time step to find the head that satisfies mass balance. To solve the routing equation, the model requires a relationship between depth and surface area. Here the model provides two primary methods for defining this geometry, each with specific data requirements and potential pitfalls. The first option is functional curve. The functional form is a Power law equation defined like this. Integrating this equation yields the volume-depth relationship utilized by the engine. This is highly efficient for standard geometric shapes. However, it lacks flexibility for natural ponds or irregular topography. The alternative option is the tabular curves, which allows the user to input a user-defined series of depth versus area data points. SWMM integrates these using trapezoidal rule to determine volume at any depth. A critical mistake here is failing to extend the table to the maximum possible depth of the node. If the water level rises beyond the highest depth in the table, SWMM typically extends the last area value vertically, treating the rest of the storage as a cylinder. If the actual pond continues to widen like a floodplain, this results in a severe underestimation of storage volume and an overestimation of flood depth. So, as we have seen, routing in SWMM isn't just a software setting, it's a modeling decision grounded in hydraulics. The key takeaway is simple. Understanding the key assumptions behind each routing option is essential for building a reliable SWMM model. In the next video, we will dive deep into the theory and unpack the fundamentals of hydraulic routing, focusing on Saint-Venant equations. If you want to truly master flow routing, that's the foundation you don't want to miss. Stay tuned.